Today we are talking about the inverse trig functions. You dealt very slightly with this in geometry, and you did a little bit more in depth last year in algebra 2. But we're looking at the inverse trig, so like the opposite of sine or cosine, in such that we would get an angle back. So we would input a ratio, and we would get an angle back. So this is not the sine matches with the cosecant. This is not this. This is where we do the true mathematical inverse. So you talked about this a couple units ago when you were dealing with your logs and your exponentials. And so for a function to have an inverse, it has to pass the vertical line test and the horizontal line test. So the vertical line test tells us if it's just a function. So for it to be any sort of function, it needs to pass the vertical line test. For it to be an inverse, it has to also pass the horizontal line test. So if we look at, say, the quadratic, y equals x squared, this one's a function because it passes that vertical line test, but it fails that horizontal line test because it does not. There are two different x values, say, -1 and +1, that both give back a y value of +1. So there are two different x values that give the same y value. So this does not have an inverse. We are going to look at our trig functions in just a minute. And we're going to try and figure out which ones, if any, have an inverse and what's true about those functions. So this is where we're going to talk a little bit about what you did in geometry. If I know that sine of theta is equal to 0.83, and I want to figure out what theta is, there's a way for our calculator to do this. And this is the same idea of what we did when we said something like, say, cosine of theta equals 1/2, and we wanted to figure out theta. And I said, if it was one of these, then it was always going to be 60, 30, or 45, because we could draw the triangle here and say, okay, cosine is the adjacent over hypotenuse, so I get my 1 and my 2, and then that's the special right triangle. So those are one of those special right triangles where I know my angle value, so I'd get that theta had to be 60. Now we're going to look at these ratios that aren't a part of a special right triangle. So theta, if I'm going to ask you to use your calculator to find your theta, it doesn't necessarily need to be one of those special angles, so 30, 60, 90. So on your calculator, to do this, we're going to hit second, and then hit the sign button. And then again, we want to make sure we're in the correct mode. So if I'm in degree mode, the answer I would get back, because your calculator would look like this, it would have sine with the -1 there, saying we're doing the inverse. If I'm in degree mode, I'm going to get a degree value back. But if I'm in radian mode, I'm going to get a radian value back. So depending on what the question is asking, you want to make sure you're in the correct mode. So go ahead, do that really fast. Here we should get back an angle value of 56.099 degrees. If I wanted this in radians, I could just either convert my 56.099 degrees to radians using that pi over 180, or we can change our calculator mode to radians and redo the problem, and we would get that our angle value is also going to be 0.979 radians. So in your calculator, they're not going to give you your radians in terms of pi, and so you won't have to give me your radians in terms of pi, which you would want to then write RAD as your unit there, just to confirm that it is in radians. But you can get it in either way. If you want an angle value that's in degrees, make sure your calculator is in degree mode. Excuse me. So we want to look at the sine function. Now this right here, this is what we call the sine wave. If we were to graph on our calculators the function y equals sine of x, we would get this, and you did a little bit of this last year, and we're going to be doing some more of this later on in this school year. We'd get this sine wave. And so looking at this graph right here, I want to know, does this function have an inverse? It is a function that passes the vertical line test. If I do a bunch of vertical lines, it's only going to cross, each vertical line only crosses exactly once. But if it's going to be a inverse, if it's going to have an inverse, I need to check the horizontal line. So because down here, I cross at not just one, but multiple points, I would say, no, my sine function doesn't have an inverse, at least not the entire function. If I take my function and I restrict it, all right, so if I take my domain and I restrict my domain, then I will have a function. So it's not one-to-one, so it doesn't have an inverse, but I can restrict it. I can cut off the sine wave. I can start it at negative pi over 2 for my x value, and I can end it at positive pi over 2. And as long as I stay within just this piece right here, I'm going to have an inverse. So that's what we do. We take our inverse sine function and we restrict it. We say, okay, if I'm going to do sine inverse, and your calculator has this restriction on it with that sine inverse, your calculator will only ever give you angle values between negative pi over 2 and positive pi over 2 when we do sine inverse. So we would say the domain for sine is restricted, or the range. So sine inverse of some ratio y, this is stuck between negative pi over 2 and positive pi over 2, which if we look on our, if we were to graph these types of angles here, that would be in which two quadrants? All right, well, 0 is in the middle there, so it's going to include this 0 line here. It's going to go all the way up to the positive pi over 2, which is 90 degrees. That's this one here. This goes up to 90. Or down to the negative pi over 2, which is negative 90. So my inverse is going to be restricted to just these first two quadrants here. So we would say sine inverse is restricted to quadrants 1 and quadrant 4. Okay, so the inverse function, got our function y equals sine of x, is represented by, we could rewrite this, and we could say x, oops, that's the highlighter, don't want that, erase, there we go. We could say x equals sine inverse of y, or sometimes we call this the arc sine, and I think I switched the blanks here. The other one was a little bit longer. But these are literally the same two functions. They just have two different names. The reason why some math teachers and some math classes use arc sine is because that little -1 there on the sign looks like it's an exponent, but it's not. It's just a label. Like when you talked about this, when we talked about f inverse of x, that was the inverse. That wasn't an exponent of -1. That's what that little -1 means. It's not an exponent, but it can be easily mistaken as one. So a lot of times sine inverse is called arc sine. Okay, so we're going to call them back and forth. You're going to see both on WebAssign. Most of the time we'll probably use the little -1 symbol because that's what we used to talk about inverses in the past. But just be aware that if you do see arc sine, it just means inverse. So we were just talking about this on the other page. Arc sine is restricted to two quadrants. It's restricted to the first quadrant and the fourth quadrant because those angles need to be between -90 and +90. So the domain for sine, we're going to restrict that the original function for sine is all angle values. So we would say this goes from -infinity to +infinity. The range, however, can only go up to 1. So we can go all the way down to -1. We can go up to +1. So that's my range. Arc sine, however, my domain and my range flip-flop. So for arcsine, my domain is going to be that -1 to 1. But my range this time, we've become restricted. So this is now going to go from that -90 degrees to +90 degrees. All right, so we're only going to be looking at these two quadrants here and here. Okay, sine, I can do any angle I want. I can do a whole bunch of angles. I can do a whole bunch of revolutions. But arcsine is going to be stuck between angles at -90 up to +90, and that's it. Okay, so it's because the inverse needs to have, it has to pass that one-to-one function test, that horizontal line test. So we restrict it. All right, so what we're going to do is we are going to try and find an angle. And so that's what inverse sine, inverse trig does. It finds angle values for us. So we've got a couple different ways. But what we're going to do is we're going to use these without our calculator. We are going to find exact value. So anytime it says, anytime it says exact values, I don't know what page I'm on. Here we go. We'll try it again. Anytime it says exact values, it means essentially without your calculator. We want it to be not rounded. We want not approximations, but we want those exact values. So the way I want to do this is I want to rewrite this problem into something that we've seen before. So remember, arcsine is just another way of writing sine inverse of -1/2, and this is going to equal to some angle. But what I can do is I can rewrite sine inverse as a sine problem. If I take that angle theta and that ratio of -1/2 and I flip-flop them, and I write sine theta, not sine inverse anymore, but regular sine theta is equal to -1/2. This is a problem that we've seen before. We did problems like this last week. So because I dealt with arcsine, that was the original question, that means I'm going to be restricted to just the first or second quadrants. I'm not looking anywhere else. I'm just looking, first or fourth quadrants. I'm not looking anywhere else. So between those two, I want to figure out where is sine negative. Sine is negative in the fourth quadrant. And so I can draw it in here and I can say, okay, well, sine is opposite over hypotenuse. So I've got -1, 2, and then this is from that 30, 60, 90, so my missing side's √3. And what I'm trying to do is I'm trying to figure out what angle goes in here. That looks like a 0. I'm trying to figure out what angle fits in here. So I want to think about, okay, it's a 30, 60, 90. I'm looking across from the -1. I'm looking across from the 1. That's 30. Now I want to think about it in terms of a standard position angle. This is standard position. I've got one line here, my terminal side here. I am opening up in that clockwise direction. So while it's 30, it's opening in the negative direction. So my theta here is -30. And that's my angle value. That's in degrees. And if I ask for it in radians, we could go through, and convert that and get -pi/3. Nope, -pi/6. I apologize, -pi/6. Okay. So when you have one of these and they're asking for the exact, so not using the calculator, rewrite it as a regular sine, regular cosine, regular tangent problem. So like this next one here, this can be rewritten as sine of theta. So sine of some angle equals √3 over 2. And say, okay, I'm stuck in the first and fourth. That's it. That's all my options are. 1 and 4. So where's sine positive? Well, it's positive in the first one. So, okay, here's my theta. Sine is opposite over hypotenuse. So that missing side is a 1. Across from the √3 is a 60. And this is opening up in that positive direction. So I'd say theta equals 60. All right. Last one here, arc sine. Arc sine of 2, that's going to equal some angle value. I don't know what angle value it is. That's what we're trying to find out, but we can figure that out. So I want to rewrite this and say that means sine of some angle value is equal to 2. So if sine of some angle value is equal to 2, that means, all right, again, this is positive. If I'm restricted to 1 and 2, that means I'm in the first quadrant. This is really like a 2 over 1. There's something wrong with that triangle right there. Something wrong with that triangle. Remember, this is a right triangle. In a right triangle, your hypotenuse has to always be the longest side. Do we have that here? No. We have the hypotenuse as 1 and my opposite side is 2. This is the reason why sine's range is restricted to being between -1 and 1. It's because if it's always opposite over hypotenuse, and your hypotenuse is the longest, that means your numerator it's small over something big, and that's always going to be less than 1. So this right here is not possible, which is why in the directions it says if possible, find the exact angle value. So we don't have it being possible there because it doesn't. If you do this in your calculator, if you try to do arc sine inverse of 2, it would tell you there was a domain error. So sine has to be equal to something less than 1, which means I can only put numbers that are less than 1 into arc sine or sine inverse. All right, so we're going to look at cosine and tangent. Again, these original cosine waves and tangent functions, they don't originally pass the horizontal line test, so we restrict the domains. Cosine gets restricted to be between 0 and pi, so that would make cosine inverse of x be between 0 and pi. Don't know why that was so hard to write. And then tangent, that one gets restricted like sine does between -pi/2 and +pi/2. So if we were to, not pi over 9, pi/2. So if we were to rewrite these in our angle values, that 0 to pi, that would be from 0 to 180. And then -pi/2 is -90 to +pi/2, +90. So that means when I look at these in our quadrant form, the inverse of cosine, which is sometimes called arc cosine, so we'd say arc cosine of y is equal to x, or we would say x equals cosine inverse of y. That one's going to be restricted to the first and second quadrant. So we're going to look at the first and second quadrant only. So cosine's domain originally is going to go from -infinity to +infinity. And the range, just like sine, goes from -1 to +1 because of the fact that adjacent and hypotenuse in a right triangle, hypotenuse is always your longest side. So just like with sine, it's small over big, which is always less than 1. That means arc cosine's domain is going to be -1 to 1. But its range, remember, that gets restricted. That's now going to be from 0 to 180 degrees, or that pi radians. So we're going to be in these two quadrants here. We're just going to be across the top here. That's all. Just across the top. So same thing with the sine, an arc sine and sine inverse. We want to rewrite this, if possible, to where, excuse me, we can have a problem like we've seen before. So this arc cosine, and this is set equal to theta. That means we have cosine of some theta equals root 2 over 2. So we want to draw that out. Now this time, I'm going to be restricted to the top two quadrants, first and second. So I want to, So what I want to do is I want to think, okay, between just the first and the second quadrants, cosine's positive in the first. So draw that out. Now this one gets a little trickier. Cosine is adjacent over hypotenuse. This is root 2 over 2. That's not a triangle that we are used to seeing. Remember, if it's possible and I want you to do it by hand without a calculator, it's always going to be 30, 60, or 45. Every single time, guaranteed. So that means this is one of those special right triangles. We got to figure out which one it is. So what I want to do is I want to think through, okay, this could have been a problem. And because there's that square root in the numerator, it's very likely that this is one of those problems that had to have been rationalized. So what I can do is I can multiply by root 2 over root 2 again. And I get 2 over 2 root 2. Or if I reduce that, 1 over root 2, which starts to look a little bit more when I do the opposite, or excuse me, the adjacent over hypotenuse, a little bit more like one of those special right triangles. So this right here, that's a 45-degree angle in there. It's opening up in the positive direction. So I get a 45-degree angle. That's my theta. We're going to skip the one in the middle. We're going to come back to that. We're going to do this one on the end here. If I make that theta, this is now cosine of theta equals negative root 2 over 2. If I go through that same process we just did, this is the same thing as negative 1 over root 2. I am again restricted to the first and second quadrants only. So I want to think about where is cosine equal to a negative. That is going to happen in the second quadrant. So that means my triangle is over here now. So it is still going to be very similar. We got this 1 root 2, but we got a negative on that one leg there. Means inside my triangle is 45 degrees. But what I want to do is I always want to look at this in standard position. So in standard position, the angle, remember, always opens up from that positive x-axis. So this right here is my angle theta. We figured out our reference angle was 45. I want to know what the angle in standard position is. So what I'm going to do is I'm going to take 180 and subtract 45, and I get 135 degrees. And you can check that in your calculator if you do. Arc cosine, so second cosine of negative root 2 over 2, you should get positive 135 degrees. Okay? So you do need to figure out what the reference angle is first, the angle inside your triangle, but I'm looking always for the one in standard position. Now, this middle problem here is a special one. This is one we haven't really talked about much in class. This is one where I want to look at, okay, cosine inverse is equal to negative 1. That's a problem because that would mean, okay, I got cosine theta equals negative 1. That's like negative 1 over 1. That means my adjacent leg and my hypotenuse are the same, which really isn't possible. But if we were to pretend that it was, if I were to draw some sort of triangle here, where my adjacent leg and my hypotenuse are the same. And I said, okay, it doesn't look like one of my special right triangles. But I could do a squared plus b squared equals c squared. Okay, so if we did a squared plus b squared equals c squared, I'd have negative 1 squared plus b squared equals 1 squared. Or 1 plus b squared equals 1. So b squared equals 0. That makes b equal to 0. So this length right here is 0. So that's not really a triangle at all. All that is a horizontal line. So if I get that cosine inverse is -1, that means my hypotenuse and my adjacent side are the same. Cosine of theta equals -1. My hypotenuse and my adjacent side are the same. I have an opposite side that's 0. So what's that's going to be is it's just a horizontal line. And I know it's going to go to the left because that's negative. So that angle there, that's my 180 degree angle. So my theta equals 180. If you have any recollection of your unit circle, you may remember that this is the point -1, 0, and x's are my cosine values and y's are my sine values. So if you remember your unit circle, this may be familiar, but it does come to the fact that if we were to consider it as to be a triangle, that would make that vertical leg, that opposite leg, 0. So it really doesn't make it a triangle. Your horizontal and your hypotenuse are laying on top of each other. So we get, it's straight west. It's that angle that's straight west. All right. Same thing with tangent. Tangent, remember when we restricted that, we said that that was restricted to the first and fourth quadrants. But again, we've got the two different functions. We could say x is equal to our arc tangent y. And remember, this was just a difference between notation. Because sometimes that little -1 symbol, which is the one you see on your calculator, but sometimes that looks a little bit like an exponent, and it's not really an exponent. It's just a label. But this is going to be in the first and fourth quadrant. So just like sine is, just like sine. All right. We do have a little bit of restrictions. We don't actually include the endpoints anymore. So tangent, remember, this one has a restricted domain. The original function does already. It has those vertical asymptotes. If you were to graph these, you would see those vertical asymptotes on our graph at all of the odd multiples of pi over 2. So 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2. So we already have a restricted domain. So for tangent here, our restricted domain, it's going to be a funky little, so I'm just going to write our super restricted one for our excuse me, for our inverse here. We go from -pi over 2 to +pi over 2, which if we did this in angles would be -90 to +90. Not inclusive this time. And then my range on tangent is actually from -infinity to +infinity. Tangent can be as big or as small as numerically possible. That means my arctangent domain, it's just -infinity to infinity. I can put anything I want into arctangent, but I can only get back angles between -pi over 2 and +pi over 2. That doesn't really look like a 2, so we're going to clean that up a little bit. That's a little bit better. Okay, so same idea. We're going to go through here. Actually, this time we're going to use calculator on the last two, and we're going to make sure that we're in radian mode for C, and we'll be in radian. No, we'll do degree mode for D. But for A and for B, we're going to do these by hand. We're going to do these by hand. So arctangent here of 0. This is the same thing as saying tangent of some angle that's equal to 0. Or I can write that as 0 over 1, right? So that means if I draw a triangle, now remember I'm restricted into that first and second quadrant, but 0 over 1, my opposite side is 0 and my adjacent side is 1. So I'm going to have this length here, that's going to be 1, but my vertical length is 0. This is not a triangle. This is just a horizontal line. So again, what is this angle? And I want it to be the angle within my restricted range here. So that's going to be, remember, we're going from -pi over 2 up to +pi over 2, that's going to be at 0. So we would say our theta equals 0. So 0 degrees, 0 radians. Now, again, if you remember your unit circle, this is the problem, point 1 comma 0. Tangent is the y over the x. So tangent would be 0 divided by 1, and 0 divided by 1 is just 0. Okay? Now, if I wanted to do tangent inverse is -1, this is a little bit more of the problems that we've been doing in the past. I would rewrite this and say, okay, this means that tangent of some angle theta equals -1, which is -1 over 1. And again, I'm restricted to the first and fourth quadrants only, and tangent is negative down in number 4. So my picture is going to be down in number 4, and tangent is opposite over adjacent. So -1 is my opposite, 1 is my adjacent. This is one of our lovely special right triangles with 45 in the triangle. But again, from standard position, this is opening up in that clockwise direction. So my angle is negative, and it is -45 degrees. Now, for our calculator, for part C, we're going to use radian mode. So make sure your calculator is in radian mode, and you can just type it in. Remember, we're going to hit second, and then tangent. Second, tangent, and then type it in. Change your mode to radian mode, and hit second tangent, -8.45, and you should get -1.453. All right, and this is remember, this is an angle value, so this is in radians. And it looks, I boxed a lot of things there, so we'll just run a highlighter through there too. In part D, we'll use degree mode. So change back into degrees. Remember, you hit that mode button, and then you can go backwards. And if we do second tangent of 3, this would give me 71.565 degrees. All right, so those are 2 that we cannot do by hand, but the rest of them we could. All right, we're going to use inverse trig to find our angle values as a function of x. So we're going to have x in our answers. So what I want to do is I want to first set up what sort of trig function is this? A sine, cosine, or tangent. So based off of that angle, this is my opposite side. 4 is the adjacent side. So Katoa tells me we use tangent. So I can set this up. Tangent of theta is equal to x over 4. What I want to do is I want to solve for theta. I want to undo tangent. I want to rewrite this as theta equals. So to do that, we use our inverse. So theta equals tangent inverse of x over 4. And that's what it means to be a function of x. It means x is in that equation. But that's it. Theta is equal to tangent inverse of x over 4. Go ahead and try and do the second one. I'll give you a little bit of time. You can pause the video and then check your answer. All right, so you should use sine. X plus 2, that is the opposite of my angle theta. 5 is the hypotenuse, and so SOHCAHTOA tells me opposite over hypotenuse. That's sine. So I set it up. Sine of theta, sine of my angle, is equal to x plus 2 all over 5. So to get theta by itself, we use sine inverse. So I get this function. Theta is equal to sine inverse of x plus 2 over 5. All right, so what we're going to do is we're going to do it with some word problems with some pictures given to us. We've got a television camera. It's on the ground, and it's looking up at a shuttle that's 525 feet from the launch pad, okay? Excuse me. It says, let theta be the angle of elevation to the shuttle, and let s be the height of the shuttle. So it's already marked on our picture for us here. Now, the picture doesn't really match the problem so much. It says 525 meters, but the picture is 750. So what we're going to do is we're just going to cross that out in the picture. and replace that with our 525. So what we want to do is we want to first part A, write a function in terms of s. So this is just like we were doing before. So we're going to look at our s, we're going to look at our 525 and say, oh, s is opposite, 525 is adjacent. So that's a tangent problem. So for part A, we're going to set it up. Tangent of theta equals s over 525. Which means, if I rewrite this, theta equals tangent inverse of s over 525. This is my function that I'm going to use to solve for my angle theta for different s values. Because the height of that rocket is changing. So when the rocket changes, the theta has to change as well. So that's part A. Part B wants us to actually find those angle values. So part B says find theta when s is 375, and then find theta when s is 1500. So when s is 325, theta is equal to tangent inverse of 375 over 525. So if we're going to do this in a degree mode, we want to make sure we're in degree mode, which we should be because we did that one problem that we put us back in degree mode, but we can always double check. And then we just want to type in tangent inverse, so second tangent, 375 divided by 525, and we should get an angle value of 56.099. We round there to 2 decimal places. And then if I wanted to figure out what theta was when s was 1500, all I'm going to do is take that 375 out, put 1500 in, and go back to my calculator again and do second tangent, 1500 divided by 525, and we would get 70.70995. If I kept going. Now you actually think I had a typo in the first one. I think I typed in the wrong thing. So if I do tangent inverse 375 over 525, we should get, I'm so sorry, I typed in the wrong ratio. This one here, that first one, should actually be 35.538. I'm so sorry. You're probably sitting there going like, I didn't get that. I was right. You were right. I was wrong. I'm so sorry. And then the second one, I believe, is correct. Just a calculator typing in error. All right. So we have these two different angles. We use our function from up above. So you always want to start with the original trig function. Tangent of an angle, sine of an angle, and then rewrite it. Okay, so always start with the original one and then rewrite it. All right, so that's it for today. Let me know if you have any questions. We're going to go over some more problems in class. Tomorrow we're going to do the law of sines, and then we have our quiz on Thursday.